All right, we're going to jump right on in to where we left off. So we already talked about the inverse of sine and cosine, and in particular the concept of taking our original function and slicing it, right, in order to create a function that will properly pass the horizontal line test and therefore whose inverse will pass the vertical line test. So we have the same situation here. If I draw a vertical line right across, I hit here, 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 and here. And as it turns out, I'm actually going to hit an infinite number of times, right? This just keeps going. So that's bad. So I need to slice it, right? I need to bound it. So one thing that we could look at is say, okay, well, what's like a good interval on which it repeats? And the answer is there's going to be a bunch. As we discussed in class, you could do it different ways, but the way that's most commonly done is to cut it off right here at pi, negative pi over 2, and pi over 2. So you just get this nice chunk of graph. So if we do this, this is what we've cut it off at. So this is we'll say this is negative pi over 3, so pi over 2 is going to be a little bit more, and similarly a little bit more than pi over 3. So the idea, remember, is that all we did was we looked at our graph of tangent up here, and we sliced it, and now we're going to grab it and regraph it down here to survey it a little bit more. So what is the domain? So where does it exist? And what we can say, or where does it exist on the x-axis? Now, it seems like we're going from negative pi over 2 to pi over 2, but there's a really interesting crucial difference here. You see, this line never actually gets to negative pi over 2. Now that's very different from before. Let's jump up a little bit and see, oh, look at this. You see, these points, right, do get to 0 and do get to pi. That's why we include this these closed brackets, right? Closed, of course, means that that it includes that. So these, because they actually hit 0 and actually hit pi, we have closed bracket 0 to pi. The problem with tangent is that, right, in our original function, because these are asymptotes, when we slice it and pull it down, those asymptotes remain. So it never actually touches negative pi or pi over 2. So we're going to use open brackets, negative pi over 2 to pi over 2, and then open bracket. Similarly, we can rewrite this as negative pi over 2 y is greater than but not equal, or y is less than but not equal to pi over 2. So this is our domain of our sliced, we'll call this our sliced tangent function. And then the range, so this is really interesting. So what's the range of our sliced tangent function? So it actually shoots up to positive infinity, right, in this direction, and shoots down to negative infinity in this direction. So our range is, well, we could write it as negative infinity to infinity, or, oh, excuse me, I apologize, this y, it's the domain, right, so this should be x, apologize for that. So here, our y goes from negative infinity to infinity. So this is our sliced tangent with a domain x between negative pi over 2 and pi over 2, but not including, right? It doesn't touch those points, and y touching all the points on the y-axis. Okay, so now we're going to play around with the inverse. So this here is the graph of the inverse. So we can see that we flipped it across the y equals x-axis. And what is the domain? Well, if the range of the original function was negative infinity to positive infinity, the domain is going to be negative infinity to positive infinity of our inverse. Similarly, because the domain of our original function was negative pi over 2 to pi over 2, that becomes the range. Oh, sorry, I did the same thing. So remember, it's a domain, so domain is in the x-axis. And then the range is the y-axis. Okay, so what this essentially means is that our function just simply never touches this pi over 2, right? This pi over 2 is an asymptote, but it's a different kind of asymptote, excuse me, down here. It's a different kind of asymptote. It is an asymptote for the y, right? It can't touch these values in the y, but whereas normally, right, we're used to it not being able to touch those values in the on the x-axis, but here it's just never going to reach this, right? If we were to keep going, it would just get closer and closer and closer and closer, closer and closer and closer this way, but it would never touch it. So that is essentially our function of tan inverse. Now for this piece right here, for the function y equals tan inverse of x, x is a number on the interval. Well, the interval for x is, negative infinity to infinity. So all real numbers, right? Any value of x is going to make sense. And y is going to be an angle, right? Remember that in an inverse function, you put in a value, you get an angle. In a regular trig function, you put in an angle, you get a value. So since it's an inverse function, we're going to input a value and we're going to get an angle. And the angle is going to be, it's a y value, so we have to look at our range. So it is from negative pi over 2 to pi over 2. And what quadrants is this going to be? All right, so if we think about our unit circle, right, we did something similar with sine and cosine, where we basically cut off our unit circle, right, in order to look for our values. So if this is pi over 2, and this is negative pi over 2, then tangent is only going to be defined, or tan inverse is only going to be defined in this, right? So we're going to cut off tangent in this section, and that's where tan inverse is going to be defined. So we just get in quadrants 1 and quadrant 4. So this is quadrant 1, and this is quadrant 4. Okay? So let's play around a little bit with some examples here. So tan inverse of root 3. So the question is, what angle, if I plug it into tangent, will give me root 3? And if you were to consult your textbook, you would get, excuse me, your textbook has, the unit circle, but if you were to consult your unit circle, you would get y equals pi over 3, because if I plug pi over 3 into tangent, I get root 3. Tan inverse of negative 1. So this would be what angle gives a tangent of negative 1. In this case, we get an angle of negative pi over 4. And tan inverse of 0, well, at 0, cosine is 1 and sine is 0, so that gives you a tangent of 0. So that means that this is just going to be 0. Or, right, yeah, just 0. Now, the final thing that we'll go over for this this section, and we've already touched on it a little bit, but we're going to go into just a bit more detail. So we already know that f inverse of f of x equals x, right? We did that on Wednesday. Similarly, f of f inverse of x equals x, right? So the idea is that they undo each other. So this is no different from sine and cosine. So we can say f inverse of f of x, where f inverse is equal to sine inverse and f is equal to sine, is equal to x. But we have to be very careful because remember, these functions are only defined in certain ways. So in order for this, our sine inverse to make sense of what's in the argument, we have to restrict this x to negative pi over 2 and pi over 2. The idea being that if x falls outside of these ranges, then sine x is going to fall outside of the range of where sine inverse makes sense, right? So the idea is that we want to make sure that whatever we're plugging into the argument is going to work, and we're going to restrict x such that we don't have these problems. Similarly, we could write this as f of f inverse of x, which in this case is sine of sine inverse of x, is equal to x. But now we have to be careful, because what are the values of sine inverse that are going to make sense? Well, we are just going to do, again, the domain, right, of sine inverse in order to make sure that our sine makes sense. So the idea is that, with this piece up here, sine is defined everywhere, everywhere on the x-axis. But remember that we want to make sure that we have a value that makes sense for sine x, and we're keeping in mind that we've had to slice sine. So I think this piece, the first one, is a little bit more, oh, what are we doing? Why do we have to restrict it? And it's because that's how we've sliced sine. We've artificially reduced the domain. Whereas in the next piece, it's like, okay, well, x is only defined for sine inverse between -1 and 1. So that's all I can plug in. So there's a couple of different ways to think about how to do these domains, but the idea is that we want to make sure that what we're plugging in makes sense when we take the outer function, and we want to make sure that we've met our domains for the inner functions. Or in this case, with our sine, we had to slice that inner function. Okay, so we can just do an example real quick. Supposing I asked for sine inverse of sine of pi over 8. All right, well, first and foremost, does this make sense? So pi over 8 does in fact fall between negative pi over 2 and pi over 2, so we're good. And at that point, all that's left is to say that we undo each other, right? These undo each other. We just get pi over 8. We could do sine inverse of sine of 5 pi over 8. And so we'll ask, does 5 pi over 8 fall within our boundary for sine of x? And as it turns out, it doesn't, right? So what this means is that we have to, right? So we say that 5 pi over 8 is not in negative pi over 2 to 2. Yeah, negative pi over 2 to pi over 2. So what do we do? Are we in trouble? Well, not necessarily. So we have to find, so we'll say find an angle in negative pi over 2 to pi over 2 such that sine of theta equals 5 pi over 8. Remember, it's a big circle, so we're trying to find, sine is going to have multiple angles are going to give the same sign. So the idea is that this 5 pi over 8 isn't good. We can't use it. But maybe there's another angle that gives the same sine value that does work. So what could that be? Well, the reference angle of 5 pi over 8 is 3 pi over 8. And as it turns out, 3 pi over 8 actually does fall within our bounds. So we can say that sine inverse of sine of 5 pi over 8 equals sine inverse of sine of 3 pi over 8. And because our 3 pi over 8 now makes sense, and we're now allowed to do this, these sine and sine inverse just undo each other. And we just get 3 pi over 8. All right, so we'll find something really similar with cosine. So how do we want to develop our sine and our cosine? Well, let me do one more example for sine. So what if I did sine of sine inverse of 0.8? Well, 0.8 in fact does fall within our domain for sine inverse, so they just undo each other and we get 0.8. Similarly, we'll go ahead and define our cosine. So we have f inverse of x is f of x, or f inverse of f of x is equal to cosine inverse of cosine of x is equal to x. But remember, we had to slice our cosine up. So only when x is between 0 and pi. Similarly, f of f inverse of x is equal to cosine of cosine inverse of x, but only where cosine inverse makes sense, and that is between -1 and 1. So we'll do a quick example. What if I were to do cosine of cosine inverse of -0.2? All right, well, -0.2 does in fact fall within our bounds of -1 and 1, so they just undo each other. And that's it.